So we're going to continue our discussion on measurements in matter, and more specifically kind of finishing off some of the information on accuracy and precision. We've talked about writing things in decimal notation. That is the preferred method. It allows us to correct for the correct number of significant digits. Easier as well. And especially with the rounding. Some of you have been doing some of the labs at home and therefore using a tape measure where it uses standard measurements, which uses fractions the majority of the time. The metric system does not use fractions, although you could do it, but 5/10 is just a lot easier just to say 0.5. 6/10 is just the same easier to say 0.6. It gets along and more complex when you're looking at 3/8 and 7/16 and some of those fractions that the standard measurements use. So that is why using the scientific method and using the SI system for our measurements is more beneficial, I think, mathematically speaking, than otherwise. And then you don't have to do any multiplying fractions. Two of the rules of rounding are very easy, very simple. The first rule of rounding, many of you already know. Maybe it's just a little bit of terminology. The first number to be dropped is less than 5. Leave the preceding number unchanged. An example. If I have the number 1.43 and I need to round that to 2 significant digits, so there would be 1 significant digit, there would be 2 significant digits. The number to be dropped, in this case the 3, is less than 5. Normally we've always said we round down, right? Technically not super correct with that. Instead, what you're doing is you are just dropping and leaving the preceding number, the 4 in this case, unchanged to just say 1.4. The second rule of rounding, very common one. If the number to be dropped is greater than 5, or 5 followed by non-zeros, increase the preceding number by 1. We have always said round up. Okay? So, example. We can see that we wanted 2 significant digits. Again, the 5 is the one that is going to be dropped. Because it's 5, we round, the 4 gets rounded up. To 1.5. The third rule of rounding is where things get crazy. It's the one that very rarely do you ever need. Okay? Many of us have never needed it to the point where you didn't even know that there was a third rule. And the reason why it happens so very rarely is what happens if you have a number, say, like that. we see and look at and say, okay, the number to be dropped, followed by maybe 5. Oh, I may will change that there. Should probably be, let's go 4, 5 on that. Followed by a whole bunch of zeros. Now, a lot of us would want to just round up, correct? But we don't. Because that rule says if the preceding number is even, you leave it unchanged. Okay? And so this one, because it's 4 is the preceding number, it's actually 1.4. Now, what's the difference between 1.45 and 1.45 followed by 4 zeros? The difference is those zeros after the 5 are significant, meaning we've made a really, really good measurement. The fact that there are no zeros after the 5 in the 1.45 indicates that we're not actually sure how far out after that goes. And so that's why we would round up. And this does become a little bit of a game for when you really kind of get into it. It's, again, not something many of you will probably ever have to worry about. Okay? So it is a rule, it is there, and so you're exposed to it so that you know about it. Some things that we will be asked to do, some simple math, such as the range, largest minus the smallest. Okay. The range tells us how far away our data points are from each other. A small range, good precision. Mean or average, many people just know the average is add up all the numbers and then divide by the number of numbers, right? There's an actual equation for it. This is what it looks like. Where you have x sub 1, or x can be anything, and so it's add all your, then divide by that number of data points by indicating the number of data points by your n. So it does have an equation. In all reality, though, what makes life even better and easier? Putting it into like numbers and or Google Sheets or an Excel spreadsheet. You can make it do all the work for you. You just have to tell it what to do. So you work smarter, not harder. And we'll kind of go through some of that, and we'll show like, oh, that's all I have to do? Yes. Then you're like, well, that's not too bad, because then it becomes a lot of copy and paste jobs. And it's not too bad. So, define some things that we do need to define, and that is precision. How close measurements are to each other. How close individual measurements are. There are two terms that get confused many times, and that is precision and accuracy. Precision and accuracy, in general speaking terms, get confused a lot. In science, there's definitely a separation. Many of you understand or have heard the concept of the measure twice, cut once. You're measuring twice to hopefully increase your precision. with that. You make bad measurements, you're going to make bad cuts. Okay? I understand that. Now, you can make good cuts off of a bad measurement. It's still not going to work, is it? Things are not going to work correctly. And so that's why that checking multiple times. Sometimes you measure twice, and if you get a different number, you're measuring a couple extra times just to make sure. Poor precision, poor technique. It's not just the lab. We talk about the lab because it's science class. Poor precision, poor techniques. We're going to later use some examples. Many of you have probably sighted in either a bow or a rifle at some point. Poor precision, meaning you're all over the target, usually means you have bad technique. The only way you can increase your precision is making your technique better. Now, your accuracy can still be off, but I always like to say is, well, at least your precision is good, at least you're wrong consistently. If you're consistently wrong, that can be fixed. It's a technique thing, or you're constantly doing the same technique over and over wrong, or if you're sighting in a scope, a couple clicks here, a couple clicks there might right the ship. The accuracy is how close they are to the true value. I like saying actual value. Why? Because then you allow word association. Accuracy, actual. What you actually want to hit. The bullseye, right? Your accuracy can be from procedural or equipment. Not having a sharp blade. Not doing a job with the wrong equipment. It's amazing on how much better my cuts when I was building our woodshed this time than last time I did one. I've increased the number of pieces of equipment that are supposed to use. So much better. So much better. Like using just like I just have a miter saw and table. I don't have a nice table saw, so I have wood horses instead of just stools. So then it bows, right? And then you're trying to like lift it and flatten it at the same time, so that your cut is somewhat correct. Put it on some sawhorse, and I was like, "Oh, this is so much better." It's like, wow. The level of craftsmanship just increased greatly at my house when we did that. All of a sudden, my wife went, I'm not really sure I trust you building that, to, oh, here's some other projects I would like to have. All right. So when we look at these examples, we have those opportunities where you can have good precision. The lightning bolts are hitting off mark, but they're close together. But they're off the mark. What is bothersome is the one on the right where you have great accuracy, bad precision. This is one that's usually seen in the lab, where you kind of do some things, you're like, yeah, and I got like 3 different numbers, but you end up like, oh, look, worked out. Every now and then, some people just get lucky. Not sure how they're doing it, but they're just like, well, I just kind of figured some things out, and it kind of looked like it was working. And that's kind of what we ended up going with. It's like, not sure how it worked out, just did. I've seen it a number of times in sports where you just look at it and you're like, how did they get that right? Hands go up and you go, I don't know. Just kind of threw it out there. Luck has sometimes its way. And yes, luck even has its place in science. But what we want to try for is good accuracy and good precision, where we're always making good measurements, good cuts. Being all over the place is not what we want. If you're doing a job and you make bad measurements, bad cuts, chances are you might be not having a job long, because they usually tend to not stick around. I sometimes also think of students in the lab that are like people that are learning how to drive a bobcat. Some people who can drive a bobcat can spin those babies on a dime and in tight places. And and people that are really good in a bobcat can do that. And people that are really good in the lab and making measurements, regardless of what it is, just run circles around everybody else when it comes to their measurements. They're able to do the measurements well and get what they need. And would be me sitting in a bobcat for the first time, just like basically playtime. Woohoo! Here we go! What does this do? And it would probably be terrible. You know, I'd need like probably an acre around me just to make sure that I didn't hit something. Now, why do we worry about this, and why do we care about a lot of the science and discovering and the relationships and observing and those things? One of the things that we talked about very early on was why do we care, or the scientific method, why do we care about it, and why do sometimes things take forever or take a long time? We have technology that allows us to do things almost instantaneously. We have technology that allows us to have school at almost any time. We have technology that allows us to have a class in one place at the same time somebody else could be 500 miles away and almost have a very small delay. We have technology that allows us to watch videos to learn things instead of what it used to be needing to know somebody to help you learn it. We have technology that allows us to do those things instantaneously. But science still takes time sometimes. Advances take time. And that, I think, becomes the why sometimes we have that problem in society as a whole of why does it take science so long to figure some things out? It's nothing to do with the fact that science is bad. It just takes time. It's part of the venting process. there are many things, that we take for granted in our everyday life that is just a part of our life. Getting a daily newspaper was a thing. Watching the evening news, or even watching the noon news, or listening to the news on the radio to get the breaking news, used to be a bigger thing. Now, you just scroll through social media on a phone to find out when somebody popular, such as Eddie Van Halen, dies. You find that almost like, whoa, hey, there it is. Then maybe it's on the news later on in a couple hours, but it's like, no, it's old news. Who cares? But it's the whole thing. It's a lot of the generation that I get to teach now, you might not have had a phone all your life, but you've had internet around you, and it might not always be the best internet, but you have so much. Even your bad internet is better than my bad internet, or even my good internet when I was your age. And it is a thing. It used to be such a novelty to have internet. Now, everything has it. There's almost so many things that don't function without it. Technology goes fast. Okay? So we want to just make sure, think about it. I think it's fun to just even think about even where you started with the first early memories of your technology, like your early computers, to what you have now. I think is extremely just a night and day. Night and day. So that is the end of Unit 0. Like I said, we will be testing on this shortly.